Here we go. All right. So we have started to talk about multiple linear regression. So as I mentioned last class, the MLR portion of the course, this is our last unit in the course. So the material that we're using, or we're going to be talking about in lecture set 13, which is the material we started on Monday and we will continue to talk about today. This is this is material that is covered on assignment 6. So it's kind of, assignment 6 is regression in its entirety, but it's split between the simple linear regression material from lecture set 12 and the multiple linear regression material from lecture set 13. Now, the biggest difference between the two is that multiple linear regression is actually the general case of simple linear regression. So in multiple linear regression, you have your response being linked to your explanatory values. So you would have like yi is equal to beta 0 plus beta 1 xi plus beta 2 x2 all the way up to beta k xk, where k can be really any number between 1 and, say, the sample size. With simple linear regression, you only have one explanatory value. So simple linear regression is actually a special case of multiple linear regression where k is equal to 1. Last class, we looked at a number of examples that illustrated a few different things. The first thing was basically just the functional form of a multiple linear regression model. So we have an example of that on slide number 6. So here we have from output yi is equal to negative 28.8768 plus 0.3227x1i plus 3.9118x2i plus 19.6705x3i. So this is basically just the regression model or the regression equation in this particular situation where we're trying to link a response variable to 3 different explanatory values. Now, in this particular illustration, as a recap, the purpose of this regression analysis is to determine if we have evidence that the response, which is the taste score of a certain cheese, can be predicted using effectively the makeup of that cheese. So its acidic value, its H2S, and its lactic value. We then talked about interpretation of the model, and we left off talking about diagnostics, so trying to assess the model fit. Now, when we're trying to assess the model fit, we determined that we required an adjusted R-squared value. The reason is every time we add a predictor into the model, the traditional R-squared will increase. So say that we have 2 models being fitted to the same data set, and we wanted to compare them. We can actually use this adjusted R-squared value not just as a tool for assessing the fit of the model, but also to determine which model gives a better fit. And this is something that we left off talking about at the end of last class. So here we had 2 models. We had a model with 3 parameters that's illustrated in In exercise 1, we had a model with 3 explanatory variables. We summarized the information in an ANOVA table and computed the adjusted R-squared. Then we knocked out one of the variables. We summarized the smaller model's information in another ANOVA table, and we computed an R-squared adjusted for that model. So in this exercise, we've seen 2 illustrations of how to compute the adjusted R-squared. The interpretation of the adjusted R-squared is the same as that of the R-squared value, but we've also seen an illustration of how we can use this tool to compare the models. Now, on the topic of model validation, the next thing that we would like to do is develop a formal hypothesis test to determine if the model we have fitted is actually useful. So to test model usefulness, we can use what is called a model utility test. This model utility test really has the same form or the same purpose as the model utility test in the simple linear regression case. So you might recall that in the simple linear regression case, we had yi is equal to beta 0 plus beta 1x. Beta 1 is the slope that relates y to x. We tested if there's any evidence that beta 1 is equal to 0. If we were able to reject the null, this implied that there was actually a value that linearly linked the response to the explanatory value. So we could say that, for example, y is going to change by beta 1 units with each unit increase in x. In the multiple linear regression case, we have multiple slope values. So our model utility test is actually a test that searches the entire system to determine if any of the explanatory values are useful as a linear predictor for the response. So the null hypothesis for the model utility test is that beta 1 equals beta 2 equals beta 3 equals beta k equals 0, which would effectively be the general conclusion that the model, well, rather, none of the explanatory variables are useful as linear predictors, right? So if the null hypothesis is not rejected, this would mean that every variable in the model has no linear relationship with the response. So this is the general test of the model not being useful at all, or that none of the explanatory variables are useful as linear predictors, which would mean that, so the model, well, the fitted regression model is not useful. And then the alternative would just be that at least one of the explanatory variables is useful as a linear predictor. So the alternative here would be that at least one beta j for j equals 1 to k is useful as a linear predictor. Actually, sorry, I'm just going to move. So we would have so the alternative would basically just be at least one beta j does not equal 0 for j equals 1 to k. For j equals 1 to k. Okay. All right, and then this is actually the same thing as saying that at least one explanatory value is useful as a linear predictor. Okay, and that would basically just mean that the fitted MLR model is useful, right? So the technical staging or setup for this hypothesis test is that beta 1 equals beta 2 equals beta 3 equals beta 4, etc., all equal to 0, against the alternative that at least one beta j is different from 0 across the entire set of explanatory variables. So you can see that this is actually very much just like a regular ANOVA. We have equality versus at least one difference. But in this case, we have equality of all slopes to 0 against at least one difference. So the general interpretation of this test would be that the fitted or the null hypothesis would state that the fitted model is not useful, because if we have no evidence to reject the null, then we're basically just saying that all of the slopes are, there's evidence that every slope should, or rather, there's no evidence that any of the slopes are different from 0. But if we do reject the null, we're saying there is evidence that at least one slope is different from 0. And that would be enough to state that the model has some usefulness, even if it's only one of the k predictors or k slopes. Okay, does anyone have any questions about that aspect? Okay, so if we want to run this test, it's going to be an F test. Now, first off, the assumptions of the F test are exactly the same as the assumptions of that we talked about for fitting the linear model in the first place. So we have the response forms a linear relationship with each of the variables. We have collected a simple random sample where each observation is independent. And then we have a constant variance assumption and the normality assumption. And both of those can be validated using residual analysis. So the assumptions of this test are exactly the same as they were when we first introduced SLR in lecture set number 12. Are the same as those discussed for SLR, with exception that y must be linear with each xj. Okay, so exact same set of assumptions. We just require that y is linear with each of the explanatory variables. But we already talked about last class how we would validate this through the pairwise scatter plots. So it's the same idea. Okay, as always, it's a 6-step test. So you can see that the hypotheses, as we discussed above, they're just a slope equality with 0 against the alternative that at least one of the beta j's in the system is not equal to 0. Significance level on step 2. On step 3, we compute an F value. This F value would be from the ANOVA tables that we designed in the previous exercise. So it's simply just we would build an ANOVA table for the fitted regression model, and then we would use that ANOVA table to find our F statistic. Then we have an F value that's on K and n minus K minus 1 degrees of freedom. So basically an F value on DF regression and DF error at whatever significance level is stated. So we can take a critical value approach or a p-value approach. All right, and then as per usual, we would just reject or not reject the null and then state our conclusion. Okay, so let's take a look at the F test for the original data set. So consider y is equal to beta 0 plus beta 1 x1I plus beta 2 x2I plus beta 3 x3I plus epsilon. Okay, where yi hat is equal to. Okay, so now we're just going to use the regression line that we fitted last class. So this is the model that we started off talking about today. And there should be a hat here. All right. All So using the information that was given to us earlier, we can construct the ANOVA table for this question. So we'll start off just by saying assume, okay, so let's just assume all are intact for, well, we'll just assume all are intact, but it's for the purpose of the question. All right, so then on the hypothesis test, we are going to have on step 1, H0 beta 1 equals beta 2 equals beta 3 equals 0 versus at HA at least 1 beta j not equal to 0 for j equals 1 to 3. And then on step 2, we have alpha equals 0.05. And then on step 3, we have F, okay, sorry. So then on step 3, we can actually use the ANOVA table from the previous exercise. So we're really just taking the ANOVA table we constructed here for this model. Right? So the values that were used to construct that ANOVA table are in that previous illustration. Okay, so we have the discussion of that from last class. So here's our ANOVA table. So we can see that the test statistic here is 16.22145. All right, so then on step 4, right, so if we take the critical value approach, I'm not going to sketch the curve this time because I'm running out of room, but this is just an F test, so everyone should be comfortable with this at this point. So we have an F value on 0.05326. Okay, so if we go to our F table, we have 1, 2, try this page. Oh, nice. Okay, so we have F 326, 0.05, 2.98. Okay, so we have 2.98, right? We know it's a one-tailed test. Our test statistic is bigger than the F value, so we can reject. If we take the p-value approach, so if we take the p-value approach, we have 326. So we're working with this block of numbers here. You can see that our test statistic is greater than the largest listed value. So that means that the p-value is going to be smaller than 0.005. And so we have p-value less than 0.005. Okay, so then on step 5, regardless of the approach that we take, we can reject H0. And then on step 6, we have at the 5% significance level, the data provide sufficient evidence to suggest that the fitted linear model is useful. All right. Does anyone have any questions? Okay. So if there's no questions, we're now going to move on to the first extension of the general model. So just again, as a reminder, we've introduced the general multiple linear regression model. And then what we've done is we've introduced diagnostic measure. Well, we talked about interpretation of the model. We talked about some diagnostic measures for the model. And now we have a general test of model usefulness based off of an F value. What we're going to do next is introduce an extension of the model that takes into account what is called interaction. Okay. Now, when we include interaction, we effectively complicate the system in some sense, but there are situations where accounting for the relationship between two explanatory variables can be very useful to us. And that's the purpose of the interaction model. Now, interaction can technically be done for any set of k variables, but it dramatically increases the complexity of that model. So we're going to talk about interaction in the simplest scenario that we can observe it, which is the two explanatory variable scenario. But just to give you some context as to what I was saying, like if you have, for example, y, x1, x2, x3, okay, this means that you could have a full model that has beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x1 x2 plus beta 5 x1 x3 plus beta 6 x2 x3 plus beta 7 x1 x2 x3. So you now have a three-way interaction. Right? So the point that I'm trying to make here is while this is possible, you can see that as you add additional explanatory variables into the system and as you consider higher order interactions, you end up considering a lot of different terms in the model. So again, the point is that this can complicate the system. And then from a technical standpoint, what this ends up doing is taking away a lot of degree of freedom from the error, which can also, in some sense, maybe muddle the result of the corresponding hypothesis tests. So we're going to talk about interaction in the simplest scenario that it can exist, which is when you have two explanatory variables and one response variable. But again, you can extend this to larger cases, but if you do that, you have to consider more interactions. All right, the general interpretation of this type of MLR model is the same as it was before. So we still have our response, which is y. We still have the predictors, which are x. We still have the slopes. In this case, the slope is relating x1 to y, x2 to y, and then relating the interaction term to y. And then we also have our error term. Okay, now the assumptions of this fitted model are the same as they were for the first order MLR. So the model we started off this lecture set with, or even the simple linear regression model, except that we're just looking for linear relationship between y and each explanatory variable. Now, with that being said, even though we have an interaction term here, we don't need to explore the linear relationship between y and the interaction. We just have to explore it between y and each explanatory variable. Okay, so only need a linear relationship between y and each xi, not interaction. Okay. All right. Now, interpreting the parameters of the model. So we're going to look at an illustration of this momentarily. But what I wanted to communicate here is that interaction does complicate our interpretation. So to try and illustrate this, we'll consider two models. So let's take our first order regression model. Okay. And then let's consider one of the scatter plots here. Okay, it's y. We'll call this beta 1. Or sorry, we'll call this x1. Okay, now, okay, well, I'll start with this. All right, so what I want to illustrate here is the relationship between y and x1 for this first model. Okay, so we have beta 0, beta 1, beta 2. Okay, so let beta 0 equal 3 and beta 2 equal 0 in the first case, right? Now, you can see here that when beta 2 is equal to 0, this leads to y equals beta, well, y equals 3 plus beta 1 x1. Okay, so if we were to sketch this line, here we have 3. Say that here, I shouldn't mark it like that. Okay, so here we have 3. Say here we have 1. Here we have 2. Here we have 3. So if we plug x1 equals 1 into the model, then we're going to get 4. Okay, if we plug x1 equals 2 into the model, we're going to get 5. And x1 equals 3 into the model, we're going to get 6. Okay, so this line here represents this model. Okay, now let's suppose that in the second scenario, we let beta 0 equals 3, we have beta 1, and then we have beta 2 is equal to 2. Okay, so now we have y equals 3 plus beta 1 x1 plus 2 times x2. Okay, actually, and then 1, 1. I guess that'll be the best way to do it based off what I'm illustrating here. All right, now, if we want to plot the relationship here between y and x1, we have, the only way we can do this is if we fix for a value of x2. Okay, so let's suppose that we let, so I'm going to use dash green lines here, dash, dash, like this. Okay, so suppose that this represents x2 is equal to 1. All right, so now when x1 is equal to 1, we have 3 plus 1 plus 2, which is 6. Okay. When x1 is equal to 2, we have 3 plus 2 plus 2, which is 7. Okay. And then when x1 is equal to 3, we have y is equal to 8. Okay. Now the point of this is to show that what we have here is a situation that regardless of the value that x2 takes on, we have a consistent slope for x1, and we have this, we basically are building sets of parallel lines. Okay, now let's watch what happens when we introduce interaction into the system. So let's take this exact same scenario as it is shown above here. Okay. So now what we have is plus beta 3 x1, x2. Okay, now if we let x2 equals 0, sorry, let me just, okay, and then up here we have, yeah, actually this would have made more sense. x2 is equal to 0. Okay, sorry, I'm just realizing that I sort of set this up wrong. But in the first illustration, what I meant to show you was when x2 is equal to 0 and you take beta 2 out of the model, or even when x2 is equal to a value, what you end up constructing are sets of parallel lines. All right, sorry about that. So this should be when x2 is equal to 0, but it's the same result. Now, what we can show below, if we consider the interaction model, when x2 is equal to 0, okay, we end up with the same model that we had above. So we have this same parallel line structure that's shown below. However, if we're considering interaction, when we let x2 equal to 1, right, we now have, okay, and then we got to set up beta 3 here. So beta 3 is equal to 2 as well. Okay, so then we're going to have 2 times x1. Okay, so when x2 is equal to 0, the interaction model and the model without interaction have the exact same form. So the red line showed in the first illustration is going to be exactly the same as the red line showed in the second illustration. But if there's interaction in the model, once you introduce that term, so let's say we let x2 equals to 1, you can now see what we have is y is equal to 3 plus x1 plus 2x2 plus, or sorry, wow, I'm making a mess of this. Like this. There we go. 3 plus x1 plus x2 plus 2 in the first case. And then in the second case, we would have 3 plus 2 plus 2x1. Okay, so that means now we have y is equal to 3 plus 2, which is 5, plus 3x1. So the interaction term is actually changing the slope of the original line. And this is the main thing that I was trying to illustrate here, despite me bumbling around. But you can see that in this case, when we include interaction, every time we let the value of one of the variables change. So when we let x2 open and be free, so for example, it's equal to 1, this is actually going to change the slope of the line of y with respect to x1. So now you can see here, 9, 10, we have 5 plus 3x1. So when x1 is equal to 1, this is going to give us 8. When x1 is equal to 2, we now have 6 plus 5, which is 11. Okay, sorry, I need to keep adjusting my scale to suit the problem. Right? So when x1 is equal to 2, we now have 11 here. When x1 is equal to 3, we have 14. So you can see that the interaction term in this case is actually dramatically changing the slope of the fitted line. I gotta get this to be straight though. Okay, I'm trying to get this to be as straight as possible. Um, yeah. Unfortunately, these points are just a bit far. There, let's see. Yeah. Sorry, the sketching kind of messes it up a bit, but the point that I'm really trying to make is just that you can see that when we don't have interaction, as you change the value of one of the variables, the effect of that variable on the slope for the other variable doesn't exist, right? So in the first case, when we don't have interaction, when I let x2 change, the slope of y and x1 is exactly the same. So regardless of the value of x2, I always have the same I always have the same slope for x1. The y-intercept changes, so the line will move up or down the y-axis, but the slope is identical. So you have sets of parallel lines. Once you include interaction in the model, you get a change in the y-intercept, but you also get a change in the slope of the variable that you are studying with respect to the response. So you can see here in the first case, when x2 is equal to 0, I have the exact same line that I sketched in the first illustration. But the second you open x2 up to be anything other than 0, once you plug that value into the line, you now have a completely different line or you now have a completely different relationship between the response and the explanatory value. So we now have y being linear with x1 by a factor of 3. So we have a much steeper regression line. And then you can imagine that if you continue to do this, so if we let beta 0 equal 3, beta 1 equal 1, beta 2 equal 2, beta 3 equal 2, okay? And then we let, x2, right? So we let x2 equal 2. Okay, so now we're going to have 3 plus x1 plus 4 plus 4x1. So that means that our line is now going to be 7 plus 5x1. So I'm going to run out of room here, but you can see like we're starting at 7. And then when x1 is equal to 1, we have 12. And then when x1 is equal to 2, you have 17, which is going to be way up here somewhere. So you can see again that the influence of the interaction is to push that slope up and up and up, which dramatically changes the effect of the line. So the point is that interaction is much more difficult to interpret because every time you change the value of one of the variables, the slope that corresponds to the other variable and the response changes with that value. So we have continually changing slopes with each value of x2 in this case, increasing from 0 to 1 to 2. And it would be the same effect going in the other direction. So if we had x1 changing, now the slope of x2 and y is going to change as a result of that. So trying to interpret the effect of that interaction parameter has to be done by holding fixed one variable at a time. And as we continually change that variable, our interpretation of the slope of y with the other variable changes, or is going to change, I should say. All right. Does anyone have any questions about that? I know that was a lot of information, but hopefully you were able to follow it for the most part. I mean, I guess, so if I had to summarize it, I'm basically just trying to say that the issue with interaction is that it interrupts the interpretations that we established before. So when we have interaction, we can no longer when we have interaction, not only do we have to condition on the other variable being held constant, but we have to take into account that every time we change that other variable, the slope of our first variable is also going to change by the factor of the interaction term. Does anyone have any questions? Right, so we're going to look at a more practical example now. So we're going to see this idea of interaction in terms of a real data set. So we'll actually have some some real numbers to work with rather than the made up numbers. And we'll be able to see how, again, that interaction influences the relationship between the other variable and the response. All right, so in the second data set, we have 32 antique grandfather clocks. And on this slide, I'm only showing the first 6 observations. But you can see here that each observation is a triplet where we have age, bidders, price. So the age of the clock, the number of bidders, and the price. And what we are interested in doing is linking age to the bidder and the price. So we're going to propose 2 regression models. One where we have age as a function of bidder and price directly, and one where we have age as a function of the bidder, the price, and the interaction between the bidder and the price. All right, so here's our pairwise scatter plot showing the relationships between the variables. So you can see that if we consider this first plot here, right, it almost looks like age and bidders really have no relationship at all. So this does not appear to be linear. But the relationship between age and price certainly does appear to be linear. So we have evidence here from the pairwise scatter plots that a linear relationship exists between age and price, but we have no linear relationship between age and bidders. So from what we would expect to see once we start to analyze the models is probably that bidders doesn't need to be included in the model, but price actually will form a linear relationship with age. And it might be the case that we can actually build a model where we only really need price in the actual modeling. Well, we only need to account for price in our linear model. Okay, so below we have output for each of the models. So this is our output for the general model. Okay, and then this is our output for the model with interaction. All right, now it's surprising because you can see here that at least in terms of assessing the individual components, okay, so in terms of assessing the individual explanatory values, it actually looks like price and bidders is significant based off the t values. So this is actually telling us that if age is included as an explanatory value, there is evidence that bidders is also useful as an explanatory value for the price of the clock. Right, so this line here is saying if age is included as a explanatory variable, then bidders is useful as a linear predictor for price. And again, the reason for this is because the p-value is telling us that we would reject h naught beta 2 equal to 0. So this p-value is saying that we have evidence that beta 2 is different from 0, which implies again that bidders is useful. So this is actually surprising based off the scatter plot, because the scatter plot really didn't seem to show that there was any relationship between price and the number of bidders. But maybe it's the case that we didn't look at it on the right scale or something, but it seemed very cloud-like. So this is quite a surprising result, actually. Okay, now when we look at the interaction model, you can see that again, it's actually very surprising what we're finding here. So this is telling us in the second line that if x1, or sorry, if x2 and x1 times x2 are in model, then x1 is not useful. So again, a surprising result given what we had observed on the previous slide. Now, the issue that we're going to run into here is if we want to include the interaction term, it would be very strange to knock out one of the main effect terms that's included in the interaction. So it would be difficult to justify removing age from the model if we are using an interaction term that depends on age. You might argue that if you scaled the data, this would be acceptable, but I think that in order to include the interaction, you also need the main effect in this case if we want to try and interpret it or have some interpretation of the effects on the traditional scale. All right. Okay, so in 1A, it asks us to state the estimated linear regression equation. So we have two. We have yi hat is equal to negative 1,336.7221 plus 12.7362x1 plus x1i plus 85.8151x2i. And then in the second case, we would have yi hat is equal to 322.7544 plus 0.8733 x1i minus 93.4099 x2i plus 1.2979 x1i x2i. Right. In part B, we're asked, does it appear like the interaction term should be included in the model? So here we can say, since H0 beta 3 equals 0 versus HA beta 3 not equal to 0 gives a p-value equal to 0.000, there is evidence that the interaction term is useful if age and bidders are included in the model. So our p-value here for the interaction term is giving us evidence to reject the null. So that means that we have evidence that beta 3 is different from 0. But this is only the case if age and bidders are included in the model. So again, each of these t-tests are conditional t-tests that assume the other variables are still going to be a part of the fitted model. So we have evidence that the interaction term should be included as long as age and bidders are both included as main effects. Okay, so on Friday, we'll continue to work through these exercises and study the MLR models. So again, what we're really doing here is just trying to get a sense of the different types of MLR models that we can construct and how we can interpret and diagnose the usefulness of these models. So we've talked about the general model, and now we're talking about the simplest MLR model that would include interaction. We've looked at how interaction affects the relationship between the response and the explanatory variable. And now we're looking at basic diagnostics of that model. Yeah, on Friday. Right. So sorry. We'll continue with this on Monday, and on Friday we'll have the quiz. Apologies. Yeah. So as always, if you guys have any questions, please let me know. And otherwise, I will potentially talk to you on Friday during the quiz, or I will talk to you on Monday.